If galaxies are fun, let's move one scale up in the hierarchy to clusters of galaxies, and let's see what we know about them. So our galaxy, like most galaxies, is part of a cluster. Our local group, as we call our cluster, is quite small. It's dominated by the three giant spirals, the Milky Way, slightly larger M31 and M33 in Triangulum, the Triangulum galaxy. And the estimated mass of this entire collection of galaxies is 4 times 10 to the 12 solar masses, of which at most 10% is baryonic, which is the name we give to normal matter, stuff where the mass is mostly protons. And so most of the mass of this cluster is dark matter, and we get that by estimating the masses of the galaxies based on star counts and gas counts and our understanding of galaxies, and comparing that to the kinematics, the Newtonian calculation of the total mass that all of this is orbiting. And based on the motion, a merger of the Milky Way with Andromeda in about 4 billion years is a distinct possibility. Of course, that won't be of too much interest to denizens of the solar system, because in 4 billion years, life here will have changed due to stellar evolution, but it will be a very interesting experience for anybody still living on some planet in the Milky Way. Note that it's not remember, a galactic collision is a stately affair. Galaxies are mostly empty space. Stars only interact gravitationally. If these were objects full of gas, there would be a lot of friction and some establishment of a combined angular momentum and a combined disk. In this case, the merger of these two these two spirals may well end up as a elliptical galaxy, because there's not enough friction to settle everything down into a disk. This is our local cluster is a very small cluster. A far more sizable cluster is the well-known Virgo cluster in the constellation, you guessed it. That has 250 large galaxies and about 2,000 smaller ones scattered over a distance of 16 million parsecs. And of these galaxies, 68% are spirals and only about 20% are ellipticals, but that includes 4 huge, giant ellipticals with a radius of between 1 and 300 kiloparsecs, so 3 or 8 times bigger than the solar system, or 12 times bigger than the Milky Way, and this includes the center of the cluster is dominated by 3 out of these 4 ellipticals. As we said, ellipticals are often found at the centers of dense clusters. And the galactic clusters, as I said, are different from star clusters in that the intercluster medium of hot gas contains on average about 8 times more mass than the sum total of all the mass of all the galaxies. About 10% of the mass, by the way, is accounted for by intergalactic stars, which were suspected but only recently directly detected. This involves detecting individual stars in a cluster, so these clusters are somewhat distant, and recently that success has been achieved. Here's a beautiful image to the right, an optical image of a cluster, Abell 2199. You see the individual galaxies shining. When you look at the X-ray image, you see that the entire cluster is glowing in X-rays because there's a large density of hot gas, and most of the baryonic mass of a cluster is in the form of gas, and this is quite important. Now, as usual, I keep saying baryonic mass because, as everywhere else in the universe, most of the mass is in the form of this mysterious dark matter. And how do we know? How do we find dark matter in a cluster far, far away? Well, we can compute the total mass. We can also use gravitational lensing by clusters to produce the mass distribution of the lens. Remember that the gravitational lensing equation that I wrote said that the deflection by which light of an angle of a beam of light passing a distance, or a distance of nearest approach r, or I think I called it b, from an object of mass m is given by this. You can imagine trying to compute what distribution of masses would cause the lensing image that we produce. It's some kind of inverse scattering problem. We see here a rich cluster along with, you can see here and there, some lensed images, and superpose this sort of blue, smooth blue over coloring is the calculated distribution of dark matter, or of the total mass of the cluster, the lensing mass, superposed on the image of the galaxies, and we see that while the galaxies show up at this distance as individual dots of light, the mass distribution is very smooth. The dark matter does not clump nearly as much as the galaxies do, and in this case it's very interestingly distributed. There's a sort of clump of dark matter at the core of the cluster, and then a ring of dark matter surrounding the cluster. The dynamics of how this happened are far from clear, I should say. And here's a map that makes the same point. This is a three-dimensional plot where the two axes are sort of along the plane of the image we were just looking at. The vertical axis is the mass distribution. We see the spikes, those are the galaxies, very dense regions of mass, but we see that most of the mass is contained, this is a different cluster, but still most of the mass is contained in the big smooth distribution underlying these individual peaks. Most of the mass of a cluster is not in the galaxies. That would be true even absent dark matter, but most of the mass of the cluster is not even in the intercluster gas, which is itself 8 times the galactic masses. It's actually in the dark matter content, which is larger still. And this brings us to one of the most pretty observations of 2006, an object called the Bullet Cluster. And there's a lot going on in this image, so let's pay attention for a second. What we see here is the process of two galactic clusters in the process of colliding and essentially merging. And the image has 3 pieces to it. There's an optical image where we see 2 concentrations of galaxies over here on the left, 1 concentration of galaxies, and over here on the right, a second concentration of galaxies. The collision occurred somewhere around here. How do we see that? Well, the pink is the glow of the heated gas, the infrared light from gas that has been heated by the collision. And this is the difference between 2 galaxies colliding and 2 clusters colliding. When 2 galaxies collide, they basically pass through each other other than gravitational dynamical friction, because galaxies are made of stars. Clusters are mostly gas. So gas, 2 clouds of gas that collide, actually interact strongly with each other and compress and heat up. So when these 2 clusters pass through each other, essentially the galaxies went through, but the gas was trapped in the middle, and so the entire gas content of the 2 galaxies is contained in those 2 pink shock-wavy glowing collections of gas. Okay, so the galaxies go through and the gas gets stuck. Where does the mass go is the question. So luckily, behind these colliding clusters are background galaxies whose lensing images we can study, and we can use that, just as we did in the previous picture, to draw a mass distribution for this object. And based on everything I said, the mass distribution, since the gas in a cluster is 8 times more massive than the galaxies, you'd expect the mass distribution to be centered in the middle, where the gas is, if it were the gas. What we see in blue is the mass distribution, and we see that the mass distribution, like the galaxies, basically went right through. Most of the mass of the cluster is not in the gas, it's in the even more massive dark matter halo of the cluster, and dark matter, being weakly interacting, sailed right through. So in some sense, the fact that dark matter follows the galaxies is paradoxically, the fact that the mass follows the galaxy is a validation of the fact that the mass is not in the forms of matter we're familiar with. In terms of those, most of the mass is in the dust. We see the dust right there in the middle. We see the galaxies and the dark matter following through. And this is a very pretty image. Some have called it a direct detection of dark matter. And this is not consistent with most modified Newtonian dynamics theories, which suggested modifying gravity. So is clusters it? The universe is made up of galaxies which fit into clusters. Well, no, there is. Follow Kant. there is a hierarchy of structures. Clusters are organized in superclusters. Indeed, our local group is on the edges of the local supercluster, of which Virgo is at 16 megaparsecs away from us, is the center. The size of the cluster is about 20 megaparsecs. At larger distances, we find more superclusters, and we can look at, try to understand the local motions relative to the Hubble flow, over and above the sort of expanding Hubble flow, and motions of galaxy clusters in the local neighborhood that we live in suggest a great attractor in Centaurus, some object with mass of 10 to the 16, I believe, solar masses. There is nothing in that region that has sufficient mass, unless it's mostly dark matter in ways we're not familiar. The Shapley supercluster over here is the most likely candidate for housing that great attractor, but it's not been observed. And so this is a map of all of the superclusters. This is a map of, I think, 100 million 100 megaparsec around the Milky Way, and we see the local region strewn with super clusters of galaxies. And now one asks, are superclusters clustered into super-duper clusters? At what level does this stop? And that's a very important question. The question is there structure at all scales? Is the universe lumpy all the way up to forever? At any size, there are super-duper hooper clusters. And to try to answer this at the largest scales, there is a famous survey that was done, which found, I believe, hundreds of thousands, or a couple of hundreds of thousands of galaxies. And this was an attempt to look deep into the sky, and in order to avoid interference from the Milky Way, the survey picked out two sort of slices of the sky that avoid interference from the galactic plane and are oriented at gaps in the galactic disk so that we can see far away without galactic interference. And they map out to z of 0.23. You can compute the distance. And the structure of these two sheets, as found by this Galaxy Redshift survey, is here. The sort of two slices are, these are two narrow angular slices that they surveyed, and as a function of distance and angle within the slice, we see here the structure of all the galaxies they found, and you see here redshift on the one hand and distance in billions of light years. This was quite a deep sky survey, and we see lumpiness. We see these structures, these sort of filaments. Remember, this is a slice, so these are presumably slices through some two-dimensional structures surrounding large, relatively empty bubbles, or so-called voids, and a sort of three-dimensional-ish representation of the way space looks in our vicinity is over on the right. And again, you see that there are these large gaps where almost nothing is, so there is structure at these very large scales. So is the suggestion here that there is structure at all levels? Well, not quite. You measure structure mathematically by something called correlation. This roughly tells you the answer to the question, if I find a galaxy or a cluster here, how does this change the probability of finding another cluster at some distance from there? And at small distances, if you find a galaxy here, then since all galaxies are members of clusters, there's very likely to be one very close to it. And this is a plot of the sort of correlation coefficient as a function, logarithmically, of distance. And we see that correlations decline. And the prediction is, from this graph, that at distances well above 100 megaparsec, correlations disappear. Correlations disappear means that if you find a collection of galaxies here, at a distance of 100 megaparsecs, it tells you nothing about the probability of finding more galaxies. So the universe at distances of, say, a billion parsec should be quite smooth, or at 500 megaparsec, exactly where you draw the line is clear. is not clear, but at large distances the universe is homogeneous. All of the perturbations smooth out at very large distances. There is not an infinite hierarchy of super duper duper clusters. At large distances we see homogeneity. Now, even so, the size of these voids is interesting. These are large regions of the galaxy, of the universe, where there are very few galaxies. How did they form? Well, we don't yet know. There are various theories of early universe structure formation. We might talk about them next week. But what is important is all of these voids have to be primordial. We are looking at the way the universe looked essentially at its creation, because in the 13 billion years since the Big Bang, there has not been time for galaxies that might have populated, or matter that might have populated these voids, to have moved out. These voids are just too large. Now, this statement that the universe is homogeneous at scales above 100 megaparsecs, or well above 100 megaparsecs, is something we will use heavily in understanding cosmological considerations next week, and it's used successfully by cosmologists, but nothing is an axiom. Recently, there has been reports of a collection of quasars, of essentially active galactic nuclei, which are scattered in what appears to be a coherent structure that is more than 1 billion parsecs across. So these black dots are this sheet of what seem to be correlated, some kind of coherent structure that is 1 billion parsecs across. That is beginning to stretch the limits of our understanding of structure formation. This is a brand new result. We'll see how it either stands up to validation, and if so, how it gets incorporated into models of structure formation. As always in this class, science is a succession of approximations to a truth. This might be the beginning of an improvement in our understanding, or it might just be a blip.